Hi, this video is about buckling. We'll be going through a problem methodologically and I'll be explaining the process as we go along. So let's start. Here's the question. A short freestanding column assembly of length 600 millimeters is fixed at the base and it consists of a channel, so this is the channel, this C bit over here, welded onto a solid plate of thickness 5 millimeters, so there's the solid plate over here, this thing. As shown. All steelwork are made from AISI 1018 annealed steel, and they give us the Young's modulus of E equals 205 gigapascal. Alright, so if we just look at this problem, this is clearly not the sideways view of it, it's probably the top view, since they tell us it is 600 millimeters, and yeah, this does not seem to be 600 millimeters. They give us a different length. So this is likely the top-down view, and then there's like a longer view. We'll probably go like this, like it's probably something like this, right? And then the top-down view or the bottom view looks like this, with the thing at the back, the other thing. Okay, so we have two sub-questions to this larger question, and that is, using a design factor of 4, find the maximum load that the column assembly can carry to avoid the onset of buckling. Then afterwards, we're going to show that any misalignment of the column greater than 5 degrees will lead to failure by yielding. So right off the bat, before we tackle these sub-questions, I'm first going to take all the information that I have about the problem. So I know that it's made from AISI 1018 annealed steel. So I go to my textbook. Okay, I go to my textbook. So this is from Shigley's 11th edition. I'm not sure if it's the international or imperial edition, so metric or imperial, but this does seem to be both, but I think it is usually both. But regardless, it is mostly the same across editions. Even in terms of editions like 10th or 9th, it should be around this mark. And we are looking at the 1018, and it's annealed, so it's hot rolled. And we are looking for the yield strength over here. I'm just double checking. I think they did obviously give it to us as well. No, they didn't. Okay, they didn't. They gave us Young's modulus, but they didn't give us the yield strength. So we do need to take note of the yield strength over here. So it's 220 megapascal over here. Okay, so we just do this right off the top of the bat. So that we have all the information ready to go. So we can then go on to the first part of the question. So this is now all our given data. We have the length, thickness, material from which we can get this yield strength. From the tables in the textbook, we have our design factor, and then we have these channel dimensions. Okay, I'm just literally reiterating the parts of the problem over here. Now that I have all the parts of my problem written out, I want to develop some kind of methodology of how to actually solve what they are asking me. What part 1 is asking me is the following. Using a design factor of 4, find the maximum load the column assembly can carry to avoid the onset of buckling. Now I've preemptively put step 1 of our entire process here, but I'm going to guide you through how I plan out my methodology. I usually kind of work from the back. So I know I'm going to have to find some maximum load to avoid the onset of buckling. So let's move on. I know I'm going to have to apply the design factor of 4 they gave me, and I'm going to apply that to some critical stress, which I need to find. That is what we're going to aim for. To find this critical stress, I need to use one of the buckling formulas. However, I don't know what kind of buckling it will undergo it, or what kind of column it is, if it's an Euler column or an intermediate column, or what it is. So what we know from our theory is that this slenderness ratio we can use to find where it lies in terms of if it's greater or less than the limiting slenderness ratio. I'm going to go through that in a moment, but the point is we know that we're going to need to find the slenderness ratio if we're going to deal with buckling. So that's kind of what I'm writing here. I know we have to going to have to apply the design factor to a critical stress. I know I'm going to have to determine the slenderness ratio. So if I'm going to find a slenderness ratio, I have two parts of that equation. I have L, the length, but I do know what the length is already. It's at 600. The other element we need to find is the radius of gyration, which is this value k. So then we write out the formula for k. K is equal to the square root of I over a. I being the moment of inertia, and a being the area. So now, can we now calculate these parts with the information we have, or do we have to break it down further? No, I think we can start from here. So this is a good place to start. Probably A. We start with A rather than I because for moments of inertia, we usually need to use elements of the areas and stuff. And since we have a composite shape that's made up of different shapes, we're going to use the area to find the centroid, which will in turn be used to find the moment of inertia. But again, if you're not totally on board at this point, we're going to be going through this. So if we put this into a nice little flowchart, this is the first thing I would write, well, the slenderness ratio and the fact that we need to find the critical stress and stuff I'd write down. But working back, we found that, okay, we have to start by finding the cross-sectional properties. Then we're going to find the composite section properties. By this, I mean things like the value of the moment of inertia and radius of gyration, and the moment of inertia and then the radius of gyration. Then we're going to find the slenderness ratio. Then from the slenderness ratio, we're going to compare it to the transition point, the limiting value for the slenderness ratio. Is it smaller than this transition point? If yes, then it's intermediate column. If no, it's a long column, or will be in the Euler region of that nice graph we have in our textbook. But from there, we find that critical stress, we apply our design factor, and then we have our answer. So, I mean, most problems are just approached this way. I usually start from the back. My exam papers are usually written the final equation here, and then I make a little arrow. Like if I, let's say E equals mc squared, just to demonstrate, right? I do this. I'm like, oh, okay, I have my value for m, and then I make a little question mark. Like it will literally be a line of this, and then I make an arrow. Okay, but I know c is equal to p for 3 to the power of pi, you know, but I don't have p, but I do have pi, and then I'll like make a little arrow, and then I'll work back like that. This is how I just do the train of thought, because otherwise a lot of times it just seems like random math that's just drawn out of the air. There is a process to it, but it's good to work backwards. Okay, so let's start. We're starting by finding the cross-sectional properties, like we said, because that's it's just a nice, easy way to start. This is the diagram that we've been given, this one over here, and in our analysis thereof, we will be breaking it up into our two pieces, even though, I mean, it's technically already broken up into these two pieces, but it's just been redrawn here to label this as one being the base and two being the channel, right? Here is our coordinate system. Our y-axis lies on their interface right here, and x is at the midpoint of the horizontal plane of the beam, right? So for step 1, we're still determining the cross-sectional properties. We're going to do the area of the base plate. That is simple enough. We know that it is a thickness of 5. We know it's a length of 76. So we just times together to get a 380 millimeters squared area, right? That is simple enough. So next, we're going to find the moment of inertia. because this is all part of the cross-sectional properties of the plate. And to do that, we go to our textbook. So this is on page 1052 for the geometric properties, because we're using a normal rectangle. And here I've just circled that this is the centroid that we're going to be looking at, which is at the value h/2, and this is the moment of inertia that we're looking at. So using those bits, we then just write them down into our on our page. Okay, so this is literally just the table from the textbook. I just want to correct myself. Yeah, I just want to correct myself here. I think before I said, oh yeah, cross-sectional properties, then composite meaning in moment of inertia. What I actually meant is that cross-sectional properties just means literally all properties of that cross-section. It is the area, the inertia, and the centroids, okay? Then the composite meaning just the total of all of them together. So the total I, the total A, the total centroid, right? Sorry for that confusion. So right, let's then return to our base plate. So we find that our final centroid location of our base plate is -2.5 because this is our reference axis that we've chosen. If it's not exactly the same, it's fine. The final answers will work out. I just want to erase this. Okay, cool, I erase it. Yeah, so this is our reference, and then from here it is 2.5. Okay, this is the magnitude of 2.5, but it is in reference from this, the negative x direction, because this is our defined positive x direction. Your own equations might be different. It just depends on what your frame of reference is. So next we're going to go on to component 2, which is our channel section. And we have these values, but I'm going to show you where we got them from. So this is what we originally have, right? We have this whole concoction over here, and then we have these values that define its dimensions. So we know we need to find the area, the second moment of inertia, and the centroid location of component 2. So we go to the textbook because they have properties of structural steel channels, all 4 standard dimensions. They have a bunch of properties because, yeah, it's a nice thing about the textbook. These are standard values. You won't be expected to work out something that complex in such a short amount of time. So I want to draw your attention to this. So this is in table A7. On the first page, it's all in imperial units, so it's in inches. On the next page, on page 1019, that's where it's in metric units, which is what we're going to be using. And here, right at the top, are your dimensions. So just look down this list for the standard dimensions. It will always be standard dimensions for your steel channels. You won't ever be expected to work it out yourself. Okay, so things that we need here are the area, and the second moment of inertia, and the centroid. You can see here on the diagram that I've included because it's on the previous page that the A value, the value 2 here is used as the axis about which we're looking at the second moment of inertia. Since we're looking at how this thing is going to be buckling over this axis, so it's going to be bending, this thing's going to be bending like that, right? And if you look at it top down, this is how you see it. Okay, so one thing I want to draw your attention to here is the units that is being used. It's centimeters for 1 centimeters, because it can really catch you in an exam. So always just make sure what units they are, and also not all of them are in centimeters. Web thickness, for example, is in millimeters. This is in millimeters. And area here, centimeter square. Okay, centimeter square over here. Just want to show you that to convert from centimeter 4 to millimeter 4, you can just times it by 10 to the power 4. But yeah, just make sure about your unit conversions. And remember, just check what units are they using here, because I'm very sure the majority of people are caught out by this because it's just such a strange thing. I don't know why they put it in centimeters, but c'est la vie. Let's move on. So this is where you get the information for this part. So we move on to the actual calculations. We literally just wrote down what we found from the previous page. We just converted it to millimeters because we're going to be working in millimeters. Okay? So next we can just add them up together to get our total areas and stuff. So we have our total area, which is area 1 plus area 2, simple enough. Our centroid location. For centroid location, we use the formula x is equal to the sum of the individual centroids times the areas over the sum of the areas. That is the formula you probably learned in second year or first year, probably first year already. But it's just a good thing to go over beforehand again, but you're going to be using this quite a bit. But this is what they're doing here. We already have the values for all of these from our previous step, so we just sub in, and it's always in reference to our defined pair of axes, and we get this. So no matter what your axes were, if you define them like this over here or here, even your final answer should also get to 7.5. 7.5 being obviously positive, and because there's no negative sign, so 7.5 millimeters in the positive x direction, so I've indicated over here. Then we move on to the total moment, second moment of inertia, and we use a parallel axis theorem for that. So we have I1 plus area times the distance, distance 1 squared, then I2, area distance 2 squared. To find these values, I've put the absolute signs here because we're going to be squaring them anyway, so it doesn't really matter if it's minus or plus. But distance 1 is 10 millimeters, so it's 2.5 plus 7.5, because it's the distance from the centroid of component 1 to the centroid of the entire area of the whole thing. Okay, so this is centroid 1, this is the overall centroid relative to that, so that's why we minus, and same over here. We sub them all in, we get our final moment of inertia. Okay, so then the next step is then to use what we have and that we've just calculated to actually sub it into the thing that we've been working towards. Well, one of the things we've been working towards. So the radius of gyration is literally the square root of the total second moment of inertia of the total area. We sub it in, we get this value. Now, we already had the length all this time. It was given to us as 600. Now we finally have this value, and we can find our slenderness ratio. And this is now where we can actually start doing the real things. Because now that we have our slenderness ratio, we can actually check our column classification, because we're going to be comparing it, our slenderness ratio, we're going to be comparing it to our limiting slenderness ratio. Its relation to this limiting slenderness ratio will determine what kind of equation we use. Okay, so I'm just going to go to the textbook to find that equation. Right. So to find that limiting slenderness ratio, this is the equation we use. Also, I tended to always write L over K limiting, because I thought this was L, or I thought it was some kind of typo, but it is actually 1. I'll show you at the end that we actually have another limiting slenderness ratio of number 2, but that's to do with eccentric loadings. It's not part of this question, but it's just something I wanted to show you later. But for now, just know this is the limiting slenderness ratio, and here is the equation we'll be using. Now, if we look at this equation, obviously this is a constant. This C is a loading condition. Okay, so we don't have this yet. We have E was given, so we can tick that off. We found our yield strength already, which was 220 megapascal already, so we've also got that. So the only thing we need to determine is our loading condition, and then we can find our limiting slenderness ratio. All right. So I've just written it over here so long, and then made a little empty space of what C should be. So to find what our loading condition C is, I'm just going to interrupt myself here. The loading condition C is the unknown that we're subbing into here. Yeah. Anyway, let's move on. Here is the textbook section. Okay, so this is in section 412. There's a table on page 209, but also the previous page 208 shows them illustrated. But this is the table you're going to be looking at, page 209. So if it's an open book exam, just put a marker on this page that this is where you go for the end conditions. Now there are 3 columns here. You never use this one. We don't care about theoretical. It's not conservative enough. I've circled this one. I'm not sure what your professor prefers, because I mean, you can't see it over here. I've blocked it a bit, but here it's like 1.2 and 1.2 over here for the recommended value. But I'd say going for the conservative value as far as I remember, but we'll just be sure to check what the preference is in the class. But in any ways, just don't use this one. So here are the different loading conditions. And in our case, we are using loading condition C, as in this figure, because it is fixed at the end. They said that the base is fixed at the end, and they did not say that anything about details of it being constrained in any way. So we know that it's then one end free and one end fixed, making this case where C is a quarter of here with a conservative value. Why I'm saying to use this table is also because these don't even indicate whether we're using the conservative recommended or theoretical values. But we can clearly see these are indeed though the theoretical values. But for sake of clarity, go with this table, and in your exam paper say I'm using table 4.2, or just in general, if you're using any table, say what table you're using. So that is where we're getting this value C from. So now that we have C, we have all the knowns. We know this, we know that, we know that. So then we can find our limiting L over K. We sub it in, and we find it to be 67.8 over here. Now, we've previously determined that our actual slenderness ratio L over K is equal to 52.4. Since this is less than our limiting one, it is not an Euler column, it is an intermediate column. If we go to the textbook on page 209 for figure 419, there's a nice figure showing the graph of how they behave. So here is our limiting slenderness ratio. If it's to the right of this, if our slenderness ratio, our actual slenderness ratio, is bigger than L over K limiting, then we can use the Euler formula for evaluating our column. But in this case, our L over K is to the left of L over K limiting. So in this case, we use the parabolic curve. The parabolic curve is governed by the Johnson formula. And the Johnson formula evaluates to this equation over here on page 211. And here is when the slenderness ratio is less than L over K limiting. Okay? So here, for still in part A, we are using the Johnson formula. This is just the same formula we saw on the previous page. Let me just go there. See? This is the exact same formula that we're just writing down over here. And our unknowns here are just P critical. We know this. We know that. We found that. We know our loading conditions. We know E. So we literally know everything. We even know our total area. So in the end, we can find a P critical. This should just be like that. We finally have our P critical. We also know that our safety factor is our P critical, or our actual load over the P maximum allowed. Okay, so just rearranging so that we get our maximum load applied, we find that this is the load applied if we have a design factor of 4. So this is the maximum load that we can apply, so that we keep within the design factor of 4 limitation. And that is literally the entire part of question A. It's just deciding what method you want to follow. Simple plug and play, 13 marks in the bag. So just to recap, this is what we did. We started with the cross-sectional areas. We used that to get the total areas and, not total areas, inertia and centroids. Then we could use those totals to get the radius of gyration. Use that to get the slenderness ratio. Then we compare the slenderness ratio with the limiting one. And the limiting one we calculated using the formula as on screen. Then we use the applicable formula to find our critical force and then apply the design factor. So that was that. Now for part B, we have this question. Show that any misalignment of the column greater than 5 degrees will lead to failure by yielding. So number one, I'm just drawing out the problem so that I can understand what they're asking and what is going on. So when they say there's a misalignment of the column greater than 5 degrees, I'm going to assume this is what they mean when they say the column is aligned. Then I'm assuming that when they say it's misaligned, then from this vertical line or vertical plane, when it deviates amount of theta, clockwise is what I'm taking, then that is what it means to be misaligned. Okay, so that's what I'm drawing here. So I made a simpler, or not simpler, a more zoomed in view of what that would look like. So here at the back is the white column. This is how it was originally, or if it were not misaligned, right? And then here it is misaligned. Here there's a very clear deviation of theta over here. But our applied force is still the exact same place. When they say misaligned, they're not saying anything else changes except the column. So there's a lot of assumptions you have to make here, and it would be good to write it down as you're going. But yeah, in this case, everything else remains the exact same. We're just shifting our column to be deviated from theta, or an amount of theta. So since we're not working in the same directions x and y as before, since we're kind of at an angle, we like we did in previous years, we just break up our main P, which is over here, into its components. P sin theta, theta being over here, is the same value over here, and then this being P cos theta, just so that we have it in terms of the same directions that align with the component we're working with, because we're going to be looking at the effects of the components of these forces on the column itself. Okay, so number one is really just drawing the problem to understand exactly what's going on. This was a bit difficult to understand what they exactly wanted, but then if you just think back a bit, just step back and really think about it, it's actually quite simple, because it's literally just saying it's 5 degrees misaligned. They didn't say anything else changes, so you can just assume everything else stayed the same. All right. So this is just identifying the critical point. So I'm assuming that the critical point is at the base. This is the top-down view, this is the side view. Side view, top-down view. Top, side, or front, or whatever. But whenever we do a failure stress state, we do want to say where it fails. What are we looking at? And the critical point would generally be the furthest point from our centroid. I mean, it's not a given rule, but it's just something. It's what it usually is. And yeah, on an edge like this and at the bottom, this makes sense. If you're literally bending something, it'll probably break here first at the base. All right. So, setting up the problem: when the column is misaligned by an angle theta, the applied load P creates two things. Okay, so we're wondering what is leading to failure. In this case, we're going to look at the stress sigma. If we look at the components of the forces we have, let me just open my pen again. It is not open. Come on. There we go. Look at the components of our forces. These are the ones that are going to be causing some kind of stress. This is going to be causing an axial force throughout the column, and therefore have an axial stress associated with that. Then if we look at this one, obviously there's probably some kind of shear going on, but that's not really what's going to be causing the yield. Instead, this is also going to be causing a moment. Okay, and this moment is going to be equal to this times this length L. And then we find what stress this moment is going to be causing. So let's look at how we're actually going to do this. So we're going to identify what stresses are caused. The axial stress is caused by the axial force. Axial meaning it acts along the axes. So this one is aligned with the axes. The drawing here might just not be entirely straight, but this is supposed to be parallel to this, parallel to this, parallel to this, parallel to this. Okay. Yeah. So we just find the axial stress, which is just force over area. Here we go. Quite simple. But in this case, we are just going to keep it in terms of cos theta, because we're just talking about an arbitrary theta right now. What we also know is that it is compressive throughout the cross section. This is quite obvious. It is literally just pushing down. Next, the other stress that we identified is bending stress caused by a moment that is caused by this. So this force times its perpendicular distance, which is length, is over here. That is the moment that's being caused. Next, any bending stress is moment times distance c. Distance c in this case, is calculated as this. This is from the memo that was given with this problem. I haven't gone into exactly why this is calculated this way. It might be that my critical point here is actually here, because this is indeed 7.5 plus 5. But yeah, just maybe looking back, it could be that it is rather the furthest point from the centroid. So I think I say the furthest point. That is probably true, but I think in this case, the furthest point from the centroid is not necessarily this side. Maybe it was this side. But I digress. I'm pretty sure this is actually the critical point. Not entirely sure about this, because it does seem like this is the distance they're talking of, because this is literally 7.5 plus 5, distance to the critical point. I'm not going to look into it too much, it's a bit late, but if you think of the answer why this, where this C value comes from, please do write it as a comment so you can help other students. But besides that, the rest of determining what this bending stress is quite simple, because this you've already calculated the second moment of inertia, and it's literally just plug and play, and you can get the final answer, which I did not write here for some reason, but it'll be on the next slide. What we do know about bending is, if we apply bending to something, it is different on one side and the other. For example, if we take something like this, if it's being bended like that, obviously this is compression and this is tension. So just to take note of, there are two kinds of stresses at play here. There's two compressions, and then there's one tensile, because this is compressive and tensile. What we're looking at now is the maximum stress, because we want to see what leads to failure by yielding. So let's take our total compressive stress now, right? So our total stress that something might need to undergo at any point is the axial stress plus the bending stress. And these are the final answers for that. On the previous page, I didn't write this is the final answer, but this would be the 2, 1, 5/4 and theta. Right. Okay. So finding this final value, we can now see this is our expression for what the maximum stress is going to be. We also have our yielding stress, which is this. Now our only unknown left here is theta, but we've said here we only need to know that anything greater than 5 degrees will lead to failure by yielding. So let's just sub in 5 degrees. Okay, well, if you sub in 5 degrees, you get this as a final answer. As you can see, even at 5 degrees, 225, 252, 225, so this should be 225.4 megapascal, is definitely bigger at 220. So even at 5 degrees, the material yields at this theta. So yes, you've now proven that it definitely, that a misalignment of the column greater than 5, because even at 5 it leads to failure by yielding. It probably yields a bit before 5, obviously, for some kind of angle, but this is sufficient and you would get your marks. So just one final note on eccentric loads. So this question is finished, but I just want to show you about eccentric loads. This is an equation you can use depending on your second limiting slenderness ratio. So this applies to when you have eccentric loadings, and you see whether or not you should use one formula or the other based on this relation. So you take your slenderness ratio, compare it to this one, and if it is bigger, you use the secant formula. If it is smaller, you can use equation 455, which is this one, which is a nice easy formula to use if you have an eccentric loading, because you only need a few unknowns and it's basically plug and play. But again, this is a lot like the Euler and Johnson formulas like before. One easier formula is valid for less than or more than the limiting, and then one is valid for less than the limiting. But in this case, the harder one is the secant formula. The secant formula is like this, and the unknowns are on both sides. So you can see unknown, 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 unknown. So you have to iterate a bit. If you're in the exam, probably don't iterate more than 2 or 3 times. I don't think it's likely that you'll be asked to use the secant formula, but yeah, just so you know, this is what it is. This is how you use it, and that is basically how you would answer an eccentric loading question, would be to identify what type it is. And again, it is defined by struts or short compression members and longer ones, but this is the thing you use to determine what equation you must apply to it. All right, and that is it. Do your best. Ignore these commas for some reason. I think I was bothered by my comma splices, but I mean, that's the way we type and talk. All the best, and do your best. Let God do the rest, because you can only do so much, and then just give the rest to God.